There is a moment in the history of life on this planet so improbable, so counterintuitive, so thoroughly in defiance of everything that the logic of evolution would seem to suggest. When scientists first began to piece together the evidence for it in the fossil record, they spent years convinced they were reading the rock wrong. Not misinterpreting a detail, but fundamentally misreading one of the most dramatic stories that the history of vertebrate life has ever produced. The story is this. Approximately 50 million years ago, after hundreds of millions of years of refinement on land, some of the most successful land mammals turned around and walked back into the sea. Not reluctantly, but successfully, completely, with a biological commitment so total that within 10 million years, their descendants had abandoned legs entirely. They had restructured their skeletons, lungs, sensory systems, and reproductive biology so thoroughly that they had become, to all outward appearances, fish. Not fish in any taxonomic sense. They were still mammals, warm-blooded, breathing air, nursing their young with milk. But fish in the way that matters most to the ocean, perfectly adapted to a life spent entirely in the water. They were the ancestors of the whales. The story of how a land mammal became the largest animal that has ever lived on this planet is the most extraordinary evolutionary story the fossil record has ever told. To understand why any animal would leave the land for the sea, you first have to understand the world that the earliest whale ancestors were living in. The world of the early Eocene epoch, approximately 55 to 50 million years ago, a world so different from our own in its climate and geography. The early Eocene was hot. Not warm, not mild, but hot, in the most extreme and global sense of the word, in a way the modern world has not experienced. Global average temperatures were 10 to 15 degrees Celsius higher than today. Polar regions were ice-free and forested, and oceans were warm from surface to depth. The tropical and subtropical regions were hot enough that the thermal limits of mammalian physiology were being tested, leaving marks in the fossil record. The Tethys Sea still existed as a warm, shallow, enormously productive body of water. Its coastlines were fringed with mangrove swamps and river deltas. This provided a gradient of environments between the fully terrestrial and the fully marine. Exactly the kind of ecological transition zone a land mammal needs to navigate. It was into this warm, ancient, extraordinarily productive coastal world that the first proto-whales, the archaeocetes, were beginning to make their first steps toward the sea. The animal that represents the very beginning of that journey, the closest thing we have to the moment a land mammal first committed to the water, is one of the most surprising animals. In 1979, Philip Gingerich found a skull in the rocky badlands of northern Pakistan. Once the shallow coastal margin of the ancient Tethys Sea, it was a mammal skull, clearly with the teeth and cranial architecture of a land-living carnivorous mammal. But then Gingerich looked at the ear bones. The ear bones of mammals are among the most taxonomically informative structures, and the ear bones of the skull Gingerich found were not the ear bones of a land mammal. They were the ear bones of a whale. He had found the skull of an animal that was, simultaneously, both a land mammal and a whale. Gingerich named it Pakicetus, the whale of Pakistan. It was, in its physical reality, deeply unlike any whale the modern world contains. Pakicetus was a four-legged animal, roughly the size of a large wolf, with long legs clearly built for terrestrial locomotion, a long tail, and a narrow skull. It had forward-pointing eyes of a land predator rather than the side-mounted eyes of a marine animal, and teeth designed for catching fish in shallow waters. It did not look like a whale. It did not move like a whale. It probably did not spend the majority of its time in the water at all. But its ear bones told the truth. Whatever Pakicetus looked like, inside its skull, it was carrying the biological legacy of an evolutionary commitment to the water. The discovery of Pakicetus answered what the earliest whale ancestors looked like. It did not fully answer why a successful land mammal would return to the sea. The answers begin with food. The early Eocene oceans were extraordinarily productive, filled with fish and invertebrates in quantities terrestrial ecosystems could not match. The land environments were intensely competitive. The sea, by contrast, was an environment of extraordinary abundance and relatively low competition from air-breathing predators. It was, in ecological terms, an opportunity, a vast, productive, relatively uncontested food resource available to any animal that could exploit it. The ancestors of the whales were ideally positioned. They were already spending time in the water, catching fish in the shallows. They were experiencing selective pressure that would reward better swimmers, more efficient divers, more fully aquatically adapted individuals with greater access to food. Evolution responds to the differential survival and reproduction of individuals. In the Eocene, better adapted individuals passed their aquatic adaptations to the next generation. Approximately 48 million years ago, the fossil record produces an animal that represents the next chapter in this extraordinary transformation. It is an animal so perfectly intermediate between a land mammal and a sea creature that when it was first described in 1994, it was recognized as a crucial discovery. Its name was Ambulocetus natans, the walking whale that swims. The name is not merely poetic, but functionally accurate. Ambulocetus was larger than Pakicetus, roughly the size of a large male sea lion, perhaps 3 meters in length, with a body mass of 100 to 120 kilograms. Its legs were still present, still functional, but profoundly different. Shorter, more heavily muscled for swimming, with large feet that functioned as paddles. Ambulocetus on land was slow and ungainly, moving with the rolling, energy-expensive gait of a modern crocodile or a seal on a beach. In the water, however, Ambulocetus was something else entirely. A powerful, efficient, and highly effective predator that moved with an undulating, spine-driven swimming motion. Its spine was long and flexible, generating thrust through vertical undulation. Its skull showed further advances toward the aquatic condition compared to Pakicetus. The nostrils had shifted slightly backward. The eyes were positioned higher on the skull, and the sensory systems for detecting movement in water were more developed. And its teeth, large, powerful, serrated, were the teeth of an apex predator of the shallow sea, capable of catching and holding large, struggling fish and other prey. There is no single moment in the fossil record of whale evolution where the legs disappear. No boundary layer in the rock, no geological horizon where an animal with legs ends and one without begins. The fossil record reveals a gradual, instructive, and extraordinary journey. A progressive, generation-by-generation reduction of hind limbs across archaeocid species over 10 million years, until fully marine whales have tiny, internal, non-functional bones, a biological memory of terrestrial ancestry. Intermediate steps are documented with luxurious completeness in the fossil record. A succession of archaeocid genera, like chapters in a book evolution wrote over 10 million years. Pakicetus, discovered in Pakistan, a pivotal chapter from 47 million years ago. More sea creature than land animal, with hind limbs poorly positioned for weight-bearing. Its tail began developing lateral expansion, the flukes, for propulsion. Pakicetus was committed to the sea. Its biological gravity shifted from land to water. The driving force was the active advantage of not having legs, hydrodynamic benefit. Legs created drag, disrupted smooth flow, and consumed metabolic resources. Generation by generation, smaller hind limbs meant better survival and reproduction. The hind limbs shrank and shrank until they were gone, a slow, patient evolutionary process. The migration of nostrils from snout to skull top is functionally significant. This change unlocked the full potential of the aquatic lifestyle for whales. In Pakicetus, nostrils were at the front, like a land mammal, positioned for terrestrial breathing. In water, forward-pointing nostrils were an inconvenience, requiring effort to breathe. Selective pressure moved nostrils back, closer to the head's top, for minimal disruption. The fossil record documents this progressive, incremental posterior migration. From Pakicetus to Pakicetus, then to derived archaeocetes, reaching the top of the head. In modern cetaceans, nostrils complete migration, becoming the iconic blowhole. The blowhole is not just a relocated nose. It's a gateway to sophisticated biological sonar. This system allows sperm whales to detect prey kilometers away in darkness. Dolphins build 3D acoustic images, and bowhead whales navigate under Arctic ice. The disappearance of legs and blowhole migration were prerequisites for aquatic life. But they don't explain the most spectacular aspect: the sheer, incomprehensible size of whales. Why did evolution make them progressively larger for 40 million years? The ocean enables gigantism in a way land cannot, due to buoyancy. Land animals must support their weight against gravity, imposing size limits. In the ocean, gravity is neutralized by buoyancy. Structural constraints don't apply. Energy saved from supporting weight is used for swimming, hunting, growth, and reproduction. This liberation, combined with the ocean's productivity, created a selective advantage for larger size. Larger whales stored more energy, allowing long migrations between feeding and breeding grounds. They could dive deeper, stay submerged longer, accessing prey smaller animals couldn't reach. Larger whales were more thermally efficient in cold water, a crucial advantage. For baleen whales, larger size meant a larger mouth and greater filtering volume. The blue whale is large because its filter feeding strategy is most efficient at that scale. It is the largest creature that has ever lived in 4 billion years of life on this planet. Size alone doesn't explain whales. It doesn't explain the sperm whale's brain. The largest brain of any animal, weighing up to 9 kilograms with neurological sophistication. It doesn't explain the complex, structured songs of the humpback whale.